Hi there. Bragg grating. What is Bragg grating? Bragg grating is an optical device which is useful for many purposes, including filtering of the light or measurement of or doing different measurements. So in Bragg grating, as you see here in this picture, we have a periodic change of refractive indices of the medium. So we have, for example, here we have two different material with different refractive indices. So what's happening in the Bragg grating as a beam of light with different wavelengths is coming toward the Bragg grating based on the refractive indices and the thickness of the medium. Some part of the light will go through the Bragg grating based on its wavelengths, and some other part with different wavelengths basically reflect back from the Bragg grating. So, and this is very useful to do different optical manipulation uh, with light. So, as you can see here, the, at different frequencies, so here this figure is plot based on the frequency. At different frequency, we can see we have a bandwidth of reflection. Basically, these bandwidths are the frequency where we have a perfect reflection, or Bragg grating is basically is acting like a mirror. Usually people talk about the first bandwidth. However, we should know that Bragg grating have many different bandwidth. And in our design, we can use other bandwidth as well for our desired purposes. But how we can calculate this bandwidth? So there are a set of equations. You see from top, we can go to down. And with these equations, we can get basically this graph, and we can design whatever we need the Bragg grating to work for and for the desired wavelengths. So here we are going to design a Bragg grating and fabricate it and test it. So based on these equations, first we have this program that's working based on this equation and can quickly calculate for us these graph that we're looking for. So for example, here in this program, as you see here, lambda 1, lambda 2 is basically is the first and basically the last wavelengths that we are interested. Number of grating is basically the number of uh, these period that we have in our grating. I will leave it as 10. Angle of grating in this program is basically telling us if the light is coming perpendicular toward the grating or with some angle. So usually Bragg grating is used for the perpendicular coming light. So I'm going to leave it as 0, which means the light is perpendicular to the grating. Next, here we have the refractive index of medium 1, N1 and N2. And at the bottom, we should basically assign D1 and D2, which D1 is correspond for the material N1 and D2 for material N2. So here I'm going to leave them as 2 micron in this program. And here, if I click on plot, okay, we can see similar to this basically reflectance for the Bragg grating, we have here the reflection at different wavelengths. And if I change for example, if I change the the size or thickness of different medium, you can see I can have I can change other parameters. So let's increase the number of grating to 20. See what's happened. Oh, you see how it becomes sharp because number of grating, as we increase number of grating, we have better and better reflection. So if I go to 50, oh, okay, so good. So that program allows us to easily design a Bragg grating at the desired wavelength that we want to have reflection. Okay, so for testing our Bragg grating, what we have here, we fabricated two Bragg grating with different thicknesses of 2 and 3 microns for both air and the medium, which is IP dip with refractive index of 1.54. And we printed this, basically these Bragg grating with nanoscribe. And here you see an image taken from the uh, those bracketing under microscope. So it's not easy to see that, but we can see the gaps and between air and the medium. Okay, so here we have tested our Bragg grating. For that, first we use an optical fiber. So in the first figure, if I go up, okay, in the first figure, what you see under microscope, we have a optical fiber, bare optical fiber, and the light is coming from this direction. And what we have here, the light that we have here is we have the fiber connected with actually 6 SLDs, and you see the light. And what you see here is the internal reflection. So most part of the light is going through the optical fiber out. However, a few percent of light reflects back. And what we measure here with the spectrometer is the internal reflection from the fiber tip. So, and you can see here we have 6 SLDs of light that the spectrometer is measuring. So now, if we look at this result, we have here the Bragg grating in front of the optical fiber, and the light was happening. The light, some part of the light, as I said, few percent of the light reflects back, and most of it go out and hit the Bragg grating. And as we saw in the design of the Bragg grating, some part of the light go through and some part reflect back. So first thing from the result that we see from the reflection, we can see here we have a very strong reflection compared to the internal reflection, which here shows us the Bragg grating is working well. A large portion of the light is reflecting back here. So the Bragg grating at this wavelength is actually acting as a mirror. While at the other wavelengths, we don't see very strong reflection. So it means the Bragg grating is allowing the light to go through. So you might think here we have kind of interference fringes, and that question can came up why we have these interference fringes here. The reason is that we hear from the Bragg grating we have two reflections, one that we had before from the internal reflection, and the other one we have from Bragg grating. That's why we see this interference fringes from the reflection, because we have two reflection and sometimes they constructively interfere with each other, sometimes destructively. However, the reflection that coming back from the Bragg grating is much stronger. So even when we have a destructive interference, the reflection doesn't go to zero. And I should say here that this interference fringes is dependent on the distance between the uh, basically fiber tip and Bragg grating. So here in next test, what we did, we increased the distance between the fiber tip and Bragg grating, and you can see here compared to the upper picture how the fringes become basically more dense. We see more ups and downs in the spectrum. Okay, so however, that is the test. But let's see if the test is in a good agreement with the results. with the results actually that was calculated from the equations or the program. So here for that, what we do, we go back to our program, and in the spectrum here we have like 1.25 micron to 1.7 micron as we have here for the range of wavelengths. So number of grating, if I go back to previous slide for number of grating, so this one is the grating that we tested with, basically 3 micron by 3 micron, and if we can, we have like 7 grating here. So if I go back to the program, so for number of grating, we have 7. And refractive index of IP dip that was used in the we use for the printing with nanoscribe, we had 1.54, and for air, 1 refractive index is 1. So for the grating, here we have 3 and 3 for both. However, here's something we should keep in mind. So if I increase the range, okay, we should keep keep in mind something, and that is the nanoscribe. Usually, due to voxel size of the in the printing with nanoscribe, usually it's a little thickness is a little larger than what we have in the design. So to compensate for that, considering the voxel size to be 150 nanometer, I added this number to the basically the thickness of the medium and reduce that from the thickness of the earth. Okay, so now here what you see here is actually the design that we obtained from the basic result that we obtained from the design. And by comparing the result, we actually can see there is a quite good agreement between the results. Here, what we have is that at the, I can say 154 maybe, we have a very good reflection. And if we go back here, we can see it's almost about 154 micron. So here we have very good reflection. And also we somehow we can see the other basically reflective band. So this one is correspond to this one correspond to this one, and this one also correspond to this one. But the reason this one is not very strong because from the beginning the light source that we sending toward the fiber wasn't strong, so we don't see very uh, a strong reflection. And here we can see how there is a good match between the design and the tested Bragg grating that was fabricated with the nanoscribe. So as I said, Bragg grating is a very useful optical device that can be used for to do different manipulation of light at different frequency. For example, here we can see how the Bragg grating, with the Bragg grating, we were just reflecting this part of the light and the other part of the light was going through. So maybe in our optical design, we can use the light that was going through to do different stuff for different measurement and many, many other things that is possible to do with this design of this Bragg grating. I hope that was full, that was useful for you, and thank you for watching.